Hello guys, welcome to Send the Mix online tutorials. On today's episode, we'll be discussing the rotation of rigid bodies. Welcome back. Now, real world bodies can be very complicated, as you all know. The forces that act on them can deform or stretch them or twist them or even squeeze them. But we often neglect this deformation for now and assume that this body have a perfectly definite and unchanging shape, but it does not. But for this video, we are going to be neglecting that fact that it has a deforming body. Well, when we talk about rigid bodies, we talk about something that is perfectly definite, unchanging, and a definite size or shape. Now, we can call this idealized model a rigid body. Do you understand what I'm saying? So now, with that being said, let us talk on what is titled angular velocity and acceleration. Are you with me? Now, when analyzing a rigid body rotating about a fixed axis, this axis must be at rest. Let us say now this is the reference frame and the body is coming around it. Now this axis must be at rest. That means this axis here must be at what? At rest, and does not change direction. It can be an iron holding a merry-go-round. Yeah, this can be an iron holding a merry-go-round, or it can be a hook on a ceiling fan. You understand what I'm saying? Now we describe this rotational. Now to describe this rotational motion, the most natural way to measure the angle is what we call radians. That is the angle at which it goes down. We can call the angle equal to S over R. When we say S is the length, the arc length. You understand what I'm saying? The arc what? The arc length over the radius of the movement. Do you understand what I'm saying here? Once we enter into examples, we get more of it. So now we talk about angular velocity. We say angular velocity W of a body is a time interval or the change of time. You understand me? We can say angular velocity W is equal to change in degree in radians over change in what? Change in time. Also, average angular velocity. Average angular velocity says change in W over change in T. W here means omega and it is representing what? Angular velocity. I want to talk about angular constant acceleration. We have some equations. Remember the equation, the 4 laws of motion equations. It also applies when you're talking about angular acceleration. The first one we have is W equals W naught plus alpha T. This is the first one. We have the second one we can still say W squared is equal to W square naught plus 2 alpha. You know what? This is the distance, but in this case the radians. Now let us go to the degree. We have degree or radians. Sorry, is half W naught plus W multiplied by T. We also have radians equal radians naught plus WT plus half. Remember this degree naught we are putting here, or radians naught, can be neglected, but for if you want to put it in a normal way for representing it, that naught must be there. But in most cases this naught is represented as 0 because it starts from rest. Once you hear that a body starts from rest, this automatically goes out of the equation, so it is automatically just 0. Are you with me there? So now we will not talk on how to find the linear speed. How to find the linear speed and acceleration of a particular point in a rotating body. Now, for example, when we wish to get the kinetic energy of a moving body in a rotational manner, we will need to find the speed for each particle in the body, because, like for instance, let's say this is a fan. Are you with me? Now this fan, the particles in this fan have their different velocities. Do you understand me? We have to find what the speed of the speed for each particle in this body. So we need the relationship between linear and angular speed, since we are about to find speed here. Are you with me? So now the relationship between the linear speed and what angular speed is represented as v is equal to rw. Now this speed, now we have the angular one which is coming this way, and we have the one which is going tangential to the circle. If you have something like this, there's a speed coming tangential to the what? To the circle. So we want to find this angular or this linear speed at that particular instant of time. But now, to get the tangential acceleration of a point on a rotating body, let us assume this point. We want to get the tangential acceleration. We say tangential acceleration, let us subscript tan is equal to r alpha. Are you with me? I'll be giving out, now in this video I'll be giving out formulas and equations to solve questions in respect to rotation of rigid bodies. So get your biro, get your pen, your jotter, your note, and get some formulas written down there. You understand what I'm saying? So now we also have centripetal acceleration of a point on a rotating body, which is the radial acceleration. We say it is equal to v square over r. This is also equal to omega square over what? R. That is for the radial acceleration or the centripetal acceleration moving on acceleration of a point on a rotating body. Now let's talk about the energy in a rotational motion. The kinetic energy in terms of the body's angular speed and in is what we call moment of inertia. Are you know what I'm saying? I said the kinetic energy in terms of the body angular speed is a new term we call what? Moment of what? Inertia. Now the moment of inertia, I, can be represented as the sum of m, let's say this is I squared. Those of you in the university must have encountered this most often in your textbook. So now the word moment means that I depends on the body's whole mass and it is distributed in space. The moment does not mean time reference moment. No, that moment there means that what? Means that I, that means this I here, depends on the body whole mass. In this case, the mass of this fan. When you calculate the particles in together, are you understand what I'm saying? So this it has nothing to do with what? Time. The moment is not to do with time. For a body with a given rotational axis and a given total mass, the greater distance from the axis to the particles makes up the particles that makes up the body, the greater the moment of inertia. What is means that, like, let us talk about this our fan. What we are saying is that for a body with a given rotational axis, the greater the distance, like the distance between this point to this point, the greater the moment of inertia. That's why sometimes once you want to screw out a bolt or a nut, you don't use your spanner must have a long width, like a long length. Like, let me give you like when you have something your spanner in this manner, your spanner must be longer. The length, like the points of rotation to the length must be long for you to have a larger moment of inertia. But if it's short, you have a shorter moment of inertia. So I would like you to take that down, take that note, because it will be given, you might be asked in your exams. Do you understand what I'm saying? So now, in terms of moment of inertia, the rotational energy of a rigid body is this. In kinetic energy now, let me write it. So now, that is half I omega squared. So I'll be giving out a comprehension. I'll be giving out the comprehension in this video now, and I want you to use the formulas that you have received in this video to solve it. Do you understand what I'm saying? I'm not going to be giving out any example today. So the formulas you've seen down, write them down and apply them to the comprehension. And you can drop your answers on the comment section. Let us observe it. Or you can come to the WhatsApp channel so we can discuss more on it. Goodbye.